Good with projectors. Okay. Probably don't need this, but the recording, which I hope they are doing, a recording. Okay. Good morning. Hey, wait a minute. There's people further back than the third row. And all the kids need to be on the front row. So kids, down here, front row, front row. There's... Okay, well, some of you might have to go on the second row. But get right here, there's two seats right here. Okay. I'm Ken Boone. KensRobots.com, something simple to remember, is my website, educational website. I do not sell anything. I just got that website so long, that URL so long ago that com was what you got. Okay. And my email is fairly easy. It's kensrobots@gmail.com. So, recently, about a couple of years ago, the IEEE, the Triangle Amateur Robotics Club merged with the IEEE North Carolina Eastern Section of Robotics and Automation Society. We both meet at the same time. People that like building robots, bring their robots and show them, and professional engineers are engineers working in robotics and automation, or just people interested in making things, come to the meetings. The meetings the first month, I think it's the next slide. Oops. Let's do it. The meetings are the first Monday of each month. They meet on Centennial campus in one of the engineering buildings. We gather for pizza. The IEEE has money. So we have pizza before every meeting, and the meetings are from 7 to 9. Usually we're in usually we're in engineering building 1, but sometimes we're not. So if you'll get on the Ken's Robots, or the Triangle Amateur Robotics Yahoo group, then you will get meeting announcements. Okay. That was the end of the advertisements. Okay. The organic robot presentation is a simple, very simple, hands-on, in classroom or in the gym or just about anywhere that you can do this presentation. Tools you need? Well, most of the times you're in the classroom and you're going to do a robotics project, so you have to get a $300 Lego, $400, well actually it's I think about $500, some of the robots that are used with the first program. But all you need for my presentation to do in the classroom is one paper bag and 3 blindfolds for every 5 to 8 students. Can you afford that? Teachers in here, can you afford that? I used to teach. I know that was about all I could afford back then. Okay, this is what got me into playing with robots. 1962. There was an article in Popular Electronics. Okay, off subject. This presentation is basically two presentations. The first hour is something that you can do anytime, anywhere as an introduction to robotics. The second part is the organic robot. Let's see what else I got here. And anyone in this room, students or adults or teachers, know enough to do this presentation. I've shown it all over the place. 2 to 3 hours. I have done the official robot in-class presentation in an hour, but it's not very good. It really takes about 2 hours. Okay. The magazine article, oops, I left it upstairs. In the March 2001 issue of Circuit Seller, which happens to be a hardware engineering type of magazine, every year they have a robotics issue, and they took my my article and put it in that, so you can go to their website and search for Organic Robot Project, and you will get their, spelling corrected, grammatically correct version. Or you can go to kensrobots.com and you can laugh at my rough draft for the article. Okay, next. Okay, in the classroom, all you need is something to write on: chalkboard, whiteboard, flip paper, a very bright light, a drop cord, and, a door or something similar to a door. Some things that you might already have, don't buy them. A compass would be neat. Ultrasonic tape measure. Every team, this is the stuff that each group of 8 students, wow, that's kind of strange the way that lined up. It's having trouble with my copy of the presentation. There we go. Okay. So, next. For the first part of the presentation, basically I'm doing things like, the very first thing I do is I ask, okay, front row, what's the definition of a robot? Y'all took too long. I haven't got 2 hours. Okay. The next question is, this was the small stuff. Is this little guy a robot? If you think it's a robot, isn't it cute? Raise your hand. Okay, you're all correct. That's not a robot. So what is it, other than a toy? Classification, what would it be? It is a machine. So let me go a couple more slides here. So this is the kind of stuff that I would be doing the first hour. What's a machine? Okay. I'm getting better. I skipped a few. This guy, Furby. This one is always fun. Is that a robot? And what is it? Well, it's a machine. But it's E.T. Don't y'all ever, you're kind of young. And this one's a real good. That stops a whole bunch. And I always loved the little hoppy frog. Okay, back to the subject. What is this? Is it a robot? Yes? No? You think it's a robot? Okay. what this is a remote control toy that several hundred of them were built in a program at Meredith College for gifted elementary school kids. We wanted them to take a robot home. But it took a lot of work, a lot of effort, a lot of prep, and dodging soldering irons when elementary kids were trying to solder it. That's bad thoughts on that. Okay. So then I would show interesting robotic pictures, including some of the automatons going back to unbelievable dates where things could write letters in script, and it was all done with a disk that programmed it mechanically. Wow. Okay, I'm back getting behind. Okay, definition of robot. That's my very simple robot definition. We've asked what a robot is. We've defined a machine. And I keep getting further and further and further. And why is a Furby just on the edge of being a robot? Well, I don't remember about that one. But the first Furby, there was a combinations of buttons you could press after it did something, and if you did that enough, and it liked to fart a lot, so you could get it to fart on command. And that's cricket again. Good grief. I'm hitting the wrong button. Okay. And there's the teleoperated. Oh, and there, that was the remote control. But a teleoperated robot is one that, like the Mars rover, where you send it a definition of what you want it to do, and it knows how to do it. Okay, I don't need to talk about that. It's actually the first, in a magazine, story of a robot that actually did something that was useful. An amateur robot. And you know how to fix this orientation problem? It's a PowerPoint that's been saved and locked. Okay, well the short of it, the very first robotic toy was a, oh I forget, very first robotic toy had buttons on it. You could tell it to go forward, backwards, shoot lasers, stuff like that. And what would happen with this one is the guy put an ultrasonic rangefinder out of a camera back then, hooked it on top of it, and set it to push the go button. The program in it was to go forward, you know, maybe 3 feet maybe, and to fire the blaster and then back up. He had a problem with raccoons under his beach house. So he set this under his beach house, pointing at the trash can, and when raccoons came by, well, you know the story. Okay, this is the organic robot part. First thing we do is brainstorm to design the robot. Okay, hopefully all of you know what brainstorming is, and I don't remember what slide that was, but you will take care of that. Okay, we'll skip the brainstorming part. Okay, if you got a robot and you're going to do something with it, well, you've got to decide what it's going to do. For the first guys, that's simple. They tell you what the robot's got to do. So in the organic robot, the robot has to get out of get to a door that has a bright light. Or it could be a bright light in the middle of an auditorium. Okay. So, and there might be furniture in the way. There might be other robots in the way. Okay. Let's design a robot. What does a robot need? Go ahead, yell. What does it need? Light sensors. Put 2 on it, then it'll know which side's brighter. Wheels, transmissions, battery, power source, controllers. Well, I usually draw a particular, oh well, this is a good one. Whenever they say to add an offensive weapon to the robot, I bring up the 3 fundamental rules of robotics by Asimov. You've got to go to the library, get this book, and read it. Got it? This book is current right now. The stuff the robots were doing in here is what we're trying to do right now. And it was written, oh, it was a long time ago. I don't remember. It's actually a compilation of a bunch of short articles that were linear. Okay, that's enough. Okay, the 3 laws, most of you know it. The robot can't hurt humans. The robot has to protect a human. And the third one is, well, the robot wants to survive, but it can't break law 1 or 2. Okay. Typical parts, that's what we were trying to do a minute ago. And I typically end up with a drawing that looks like this, because I'm drawing it and they're hauling out parts. And notice that the computational unit's not in the robot, because it's kind of heavy. Okay. The next thing we need is a robot control language. And I'm not talking about the little software down deep that says turn on port 7 to make the motor go forward. What I'm talking about is what the big subroutines would be. One would be turn toward the light. That would be a whole lot easier if you had a subroutine turn toward the light, other than, well, I got to turn right until both of them are bright, are the same brightness. Okay, so somebody add 2 commands. Okay, why is go forward not correct? Tell me to execute go forward. Well, go forward, okay. I will do that till my battery runs out. So, you need a forward to interrupt, or you need a forward distance. This is a big robot, so it's done in feet, the distance. And turn, it's the same thing. You got to tell them turn clockwise. So, and I like Boogie. That's, yes, I did it! Okay, the next thing is the students are divided into teams of 5 to 8. 8's better, but closest you get to 8 the best. Okay. I'm going to talk about programming. Old geezers like me, we would flowchart our program before starting to write it. As I get older, I need to flowchart the program so I'll remember what I'm writing. But flowcharting is basically you have things you're going to do in a box, decisions you want to make in a triangle, and little arrows that attach them all together. Now, that's a simple one. If the robot had a compass, you tell it to turn north. Wherever north is, go forward 2 feet and turn toward the light. So the projector's the light. Okay, the next one has a decision to make. You check your ultrasonic rangefinder. If it's greater than 2 feet, you go forward 1 foot. And you keep doing that until you're within 1 foot of something. Okay. This is a program that will work, which I do not show them. And typically with the younger it goes, the less successful the programs are, but that's basically the logic. Okay, I need 4 volunteers. The first 4 on the front row. Right up here. Okay, who's tallest? Over you, front and center. Are you ticklish? Great. Okay. You need to put your arms out straight and hold them right there. In a safe height, out straight. You need to be out straight. It's okay. Okay, you take your arm and put it around that arm and hold it like that, and you're on the other side. Just like that. Wow, they take great instruction. Okay, you are the robot. You are the sensor platform. Oh, you're illuminated. Okay, and you can tell, well, there's the bright light. You're also locomotion, your power, your communication, and you're the front line. So you need to see just a little bit. So you wear that. Okay, you think that's funny? The bumper, the locomotion, the power source doesn't need to see. So you would be wearing a light. You're the right bumper, rear bumper, left bumper. Okay, so this is the robot. And I got in trouble at TIP because they have, well, I did the summer residential where I taught a robotics class during the summer, but they have weekend experiences where they come one day. I wrote in the experience that they would take home part of a robot. They got real mad when the part of the robot was them. Okay, come up here. Okay. You are the computational unit. And obviously, you're too heavy for the robot to carry. You're going in another room where you cannot see the robot and interpreting your program. You holler out one command, which happens to be turned toward the light, so the robot would at this point say ready, and check bumpers. Well, none of the bumpers, so the command would make the robot say that none of the bumpers are touching, and it would go through. Now, if there's more than one robot, the controller number 1 would give one command for robot number 1. Controller number 2 would give one command for robot number 2, and you would start going in a circle, one command at a time. Well, it's really funny when these robots start bumping into each other, because nobody ever figures out, well, I got to have something for, I bumped into something backwards. Okay. The robot can be dismissed. Go home. Okay. Okay, before, you have to do some setup. So there's the drawing. There's some of my past robot. Actually, for first teams, I was invited to go up to Erie, Pennsylvania, because the company I worked for, that's its home base, and the president wanted me to go up there to do this presentation, and it was a gathering of all the first teams in Pennsylvania. And this was a long time ago, so there wasn't, maybe 4 teams, but I did this in a gymnasium with, I don't know, it might have been 10 robots. And that was wild. And plus, I really couldn't do one robot command at a time, so they were all hollering back and forth. It was a hoot. Okay. There's actual organic robots. to set up for the room, you need to make a drawing of the activity area where you're going to be. Put it on a flip chart. Pre-locate the organic robots so they don't know where they're at. And then you start doing the commands. Okay. Okay, we've done that. Okay, this is an interesting side project. It could be a whole another thing you do with your students. With the organic robot, you actually, what's my time? Woohoo, my time's running out. I'm stomping on my robot. Something you can do with the organic robot is simulate Mars rovers. So instead of me standing in a doorway and repeating the commands from the robot to the robot and from the replies from the robot, take a tape recorder and have the controller or the computational unit record the next command. Then send somebody to another building where the robot is and execute the command. Now, you'll probably be doing that quicker than actually doing it on Mars, because when Mars is the closest, it takes 6 minutes for a command to get there. And then it has to do its thing, and then it's 6 minutes to get back. And another thing you could do, which is legitimate for Mars, is you could take a little video recorder and see what the robot did, so you would, as feedback. Okay. Let's talk about that. This is my organic robot simulator. Here it is. I think it was about 2000, I forget, but about over 10 years ago, probably over 15 years ago, Duke TIP program, which is for high school students. The summer residential program is for high school students that did 99.75 in math on the SAT. A very gifted and unusual group. It's wild when I would go into the cafeteria with them, and they would be talking about, you know, quirks and black holes, you know, stuff you wouldn't expect from a high school kid. Okay, get back to this. In the class, they're in the class, what is it? I forget. It's on the slide. They're basically in the class 3 weeks. And for those 3 weeks, Monday through Friday, they're in the classroom 7 hours a day. For some of the other classes that they teach, they actually get college credit for taking the class. Okay, so I designed this robot for the class. It is not a kit. They build it from raw materials. They did sawing, they did soldering, they put the circuits together, they assembled it, they modified the servos so they would go all the way around. Okay. There's some of the kids working on the robot base, and there's mechanical drawing. Engineering at its finest. There's other assembly tasks going on there. There's programming going on. And the first thing they have to do after they program it is do a program that does something interesting. There's a bright light in the middle of the room. They had killer robots. They had robots that would avoid the light. They had robots that would do a descending circle. Well, that was neat. Okay. The next thing they do, for the next 2 weeks, they build an international robot home firefighting robot. They're divided into teams of 4. This is a competition that adults take a year to build a robot to do it. But they were all fairly successful. There's their robots they built. And there's part of the firefighting contest arena. Those 2 are 2 of my robots. There's my first team. The first team I worked on at the Nationals. And that's me when I built my first robot. Isn't that cute? That was in the State Science Fair. And you can get a hold of me, kensrobots.com. I'm active in amateur robotics, US First, radio control, including waypoint-enabled fixed wing, amateur radio, and spend a lot of time helping my wife at her 2 churches. Graduated from NC State University, actually as a teacher, industrial arts teacher, and taught in Wake County, and then went out into industry for the last 35 years of me. There's the references, and that's the end. Every class, if we could raise the money, would do a t-shirt